Pluto, a far-off and befuddling body, was once thought to be a solitary and veritable planet, an individual from our planetary family. However, recent revelations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking disclosure. They suggested that this cold world is on a potential crash course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing a fascinating cosmic anomaly, or is there more to this impending celestial incident? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a lesser status, remains a subject of interest and study in the astronomical community. According to precise calculations by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are raising the alarm about a potentially catastrophic event between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unusual compared to any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, meaning that since its discovery in 1930, it has yet to complete even one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is characterized by its highly eccentric shape, vastly different from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination of 17 degrees to the ecliptic plane. The path Pluto follows is significantly more unpredictable compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. Perhaps one of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's orbit. For approximately 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, contrary to what one might expect based on their positions in the planetary system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers attempted to explain its unusual path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto stood apart with its extreme inclination and irregular shape. The mystery surrounding Pluto's orbit can be explained by the three-body problem in celestial mechanics. This problem involves understanding how three objects in space, such as Pluto, Neptune, and the Sun, move and interact with each other through their gravitational forces. Predicting their movements is complex, as each body continuously affects the others. For Pluto, this problem reveals how its orbit, Neptune's orbit, and the Sun's gravity all interact in a highly intricate manner. Terms like asymptotic libration, scope libration, and the VZK wobbling are crucial to solving this puzzle. According to astrophysicists, what keeps all planets in their orbits is a form of libration. In Pluto and Neptune's case, this means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from interfering with each other. Degree libration, on the other hand, refers to the vertical motion of a celestial body in its orbit. For Pluto, this suggests that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding another layer of protection from potential collisions. Another critical factor in this scenario is the VZK wobbling, named after three scientists, VA, LV, and KU, who studied how celestial objects move in space. This concept explains how Pluto, Neptune, and the Sun's gravitational pulls affect each other. The VZK wobbling helps us understand why Pluto's path near the Sun is so peculiar. Despite its apparent randomness, this phenomenon helps keep Pluto's orbit stable over incredibly long periods. The VZK wobbling demonstrates that, although space might seem chaotic, certain patterns and forces work together to maintain order. These factors ensure Pluto's orbit remains stable, preventing it from colliding with Neptune or veering off course. This three-body problem plays a fundamental role in our understanding of planetary orbits, particularly how celestial bodies influence one another. Focusing on this helps us study Pluto, our neighboring planetary system, and distant stars and planets. Numerical simulations in the late 1980s revealed that, despite these predictable properties, Pluto's orbit still exhibits small deviations in initial conditions, leading to significant differences over long periods. However, these peculiar characteristics of Pluto's orbit have been found to maintain stability over extremely long timescales. Later computer models have helped scientists understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Interestingly, Neptune and Pluto share a unique resonance. For every 2 orbits Pluto completes, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only factor at play. Jupiter's gravity also plays a crucial role in safeguarding Pluto's orbit, while Saturn contributes as well. Studies show that Jupiter's gravitational force alone is strong enough to keep Pluto on a stable course for an extraordinarily long time, possibly even billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto can continue orbiting safely without running into trouble. These orbital irregularities are essential in the larger context of the universe for maintaining the stability of celestial bodies. Without these gravitational interactions, our solar system would be far more chaotic and unstable. Bodies like Pluto could indeed collide with others or be ejected from their orbits, triggering a domino effect on other celestial objects. For Pluto, especially with ongoing discussions about its potential collision with Neptune, understanding its orbit is crucial. This research provides us with a clearer picture of the dynamic nature of planetary systems. Pluto's case illustrates that even in seemingly unstable orbits, equilibrium can be achieved through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these anomalies to better understand our place in the universe. Exploring the vastness of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital resonance, which implies the delicate dependence off-orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight changes in Pluto's position or speed could significantly alter its long-term orbit. Advanced computational simulations have been crucial in helping scientists understand how Pluto moves through space. These models use complex mathematics to simulate how Pluto, along with other celestial objects like Neptune, exerts gravitational forces on one another. By tweaking minor details in these simulations, astronomers can observe how even small adjustments can have a massive impact on Pluto's trajectory. In the late 1980s, these simulations revealed something fascinating about Pluto's long-term orbital evolution. Despite its eccentric and seemingly unpredictable path, the gravitational interactions with Neptune and other giant planets keep its orbit remarkably stable over immense timescales. However, even with this stability, small perturbations in the solar system could introduce chaotic variations in Pluto's trajectory over millions or even billions of years. This raises a crucial question. Could a future astronomical event disrupt Pluto's orbit enough to put it on a collision course with Neptune, or even eject it from the solar system entirely? To answer this, scientists have conducted extensive gravitational simulations that account for factors such as planetary alignments, shifts in Neptune's orbit, and even the influence of distant celestial bodies like passing stars or rogue planets. These simulations suggest that while Pluto's current orbital resonance with Neptune is stable, external forces could gradually alter this delicate balance. One potential factor is the gravitational influence of passing stars. Our solar system is not static. It moves through the Milky Way, occasionally encountering other stellar systems. If a sufficiently massive star were to pass nearby, its gravity could subtly perturb the orbits of the outer planets, including Neptune. Even a minor shift in Neptune's orbit could disrupt its resonance with Pluto, potentially leading to long-term orbital instability. Another concern is the Yarkovsky effect, a subtle but significant force caused by the way Pluto absorbs and re-emits solar radiation. Over millions of years, this effect could gradually shift Pluto's orbit in unpredictable ways, adding another layer of uncertainty to its long-term stability. Additionally, Kuiper belt interactions may play a role. Pluto is part of the Kuiper belt, a vast region of icy bodies beyond Neptune. If a large Kuiper belt object, KBO, were to pass close to Pluto, or if Pluto experienced a collision with another KBO, its orbit could be slightly altered. While these changes would be minor at first, over millions of years, they could add up to significant deviations in Pluto's trajectory. Despite these possibilities, current models suggest that Pluto's resonant lock with Neptune will likely persist for at least another billion years. However, beyond this timescale, predicting Pluto's exact fate becomes extremely challenging due to the chaotic nature of gravitational interactions in the outer solar system. What would happen if Pluto and Neptune did collide? If an extreme event were to push Pluto out of its stable resonance, leading to a collision with Neptune, the consequences would be cataclysmic, though mostly for the two bodies themselves. Pluto, being significantly smaller than Neptune, would be completely destroyed in the impact, breaking apart into a vast field of debris. The energy released in such a collision would be equivalent to millions of nuclear bombs detonating simultaneously, generating an enormous explosion visible across the solar system. The debris from the impact could form a new ring system around Neptune, similar to Saturn's rings, but composed of shattered remnants of Pluto. Some fragments might be ejected outward into space, joining the Kuiper belt, or even escaping the solar system entirely. Others could be pulled inward by Neptune's gravity, eventually falling into its atmosphere. Could such an event impact Earth? Although a Neptune-Pluto collision would primarily affect the outer solar system, it's possible that some debris from the impact could be ejected on trajectories that bring them toward the inner solar system. If even a small fragment were to be pulled into Earth's gravitational influence, it could lead to a significant asteroid impact event. However, given the vast distances involved, the likelihood of such debris reaching Earth is extremely low. More realistically, the event would provide an unprecedented opportunity for astronomers to study planetary collisions in real time, offering valuable insights into the formation of moons, ring systems, and even planetary atmospheres. Could Pluto be ejected from the solar system entirely? Another possibility, though less likely, is that instead of colliding with Neptune, Pluto could experience a gravitational interaction that flings it out of the solar system. If Neptune's gravitational pull were to accelerate Pluto past a critical velocity, it could become a rogue planet, wandering the galaxy without a star to orbit. If this were to happen, Pluto would become a frozen, lifeless world drifting through the interstellar void. Without the sun's warmth, its surface temperature would plummet to near absolute zero, and its thin atmosphere would collapse into ice. It would no longer be part of our solar system, instead becoming a lonely traveler in the vastness of space. Conclusion. What does this mean for Pluto's future? For now, Pluto remains in a stable orbit, safeguarded by its unique resonance with Neptune and the gravitational influences of other planets. While the possibility of a future collision or ejection exists, current models suggest that Pluto will remain in our solar system for at least the next billion years. However, as we continue to refine our understanding of celestial mechanics, new discoveries could change our perspective on Pluto's ultimate fate. Whether it collides with Neptune, gets ejected from the solar system, or continues its mysterious journey in its eccentric orbit, Pluto will always remain one of the most intriguing objects in our cosmic neighborhood. One thing is certain, the story of Pluto is far from over. Notwithstanding having frameworks like ASM, todic libration, and expansion libration to settle it, its circle can in any case be ridiculously sporadic. On the off chance that you start with even a slight distinction in where Pluto is or how quick it's moving over numerous years, its way could wind up looking totally different. Notwithstanding this disorder, Pluto's circle stays stable for billions of years. This recommends that Pluto's excursion around the Sun has a specific request to it, despite the fact that it appears to be tempestuous from the get-go, particularly when it involves sporadic circles like Pluto's. This presents colossal challenges. The inherent nature of these frameworks proposes that long-term forecasts are frequently loaded up with vulnerabilities. While mathematical recreations are a fundamental instrument for understanding and anticipating what's in store conduct of heavenly bodies, they too highlight the constraints of our conjectures. These models depend vigorously on the exactness of introductory circumstances and the intricacy of the connections they reenact. Any slight slip-up or deviation can radically change the outcomes, making exact expectations and overwhelming tests. Furthermore, the fierce nature of huge circles like Pluto's fills in as a sign of the ever-changing and dynamic nature of the universe. While we've made huge steps in understanding space, Pluto's model helps us to remember how our comprehension of the universe is still restricted. Understanding the gravitational impacts of the giant planets on Pluto's circle offers significant insights into the more extensive dynamics of the nearby solar system. It shows how the presence and position of every planet can have sweeping consequences for the steadiness and bearing of different bodies inside the framework. So, for what reason are conspicuous astrophysicists suddenly raising worries about a possible impact among Pluto and Neptune, in spite of all of these complicated powers attempting to forestall such an occasion? Neil deGrasse Tyson, a popular astrophysicist, offers a book-length viewpoint on the secrets of our nearby planetary group, especially the intriguing illustration of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, gives sagacious analysis on the evolving nature of heavenly mechanics and the public's interest in the neglected corners of space. His position on Pluto's renaming is outlined in the steadily growing information on our solar system. He sees the renaming not as a diminishment, but as an important change in understanding. With our developing comprehension of the many bodies surrounding our Sun, Tyson's approach to heavenly mechanics is one of constant learning and change. He sees the intricacy of Pluto's circle, as well as its interactions with Neptune, from a perspective that recognizes the unpredictability of space. He suggests that while Pluto's circle is stable for the time being, it could go through massive changes in the future. This chance serves as a sign of how much we still need to discover about the forces shaping our nearby planet group. In the grand scheme of things, Pluto's circle is a captivating case study in the complex interaction of gravitational forces within our nearby planetary system. While its circle is stable right now, the mysterious dynamics between Pluto, Neptune, and the different planets suggest that even the most apparently stable orbits could change over time. As astrophysicists like Neil deGrasse Tyson continue to research the mysteries of the universe, they help us better grasp the delicate equilibrium that governs the movements of heavenly bodies. The potential for a Pluto-Neptune crash isn't necessarily unavoidable, but it serves as a reminder of the continually evolving and confusing nature of the universe. In spite of the established theories surrounding Pluto's orbit, it's important to consider the broader implications of these dynamics for how we understand the nearby solar system and the universe at large. While Pluto's journey is one of curiosity, it is also a reminder that the universe is filled with mysteries and complexities waiting to be explored. The concept of orbital resonance, particularly between Pluto and Neptune, is a central part of the riddle. This resonance, where the ratio of Pluto and Neptune's orbits is 2 to 3, is a fundamental aspect of divine mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance ensures that despite their orbits crossing, the 2 planets never impact. This is a result of the gravitational interactions that stabilize their paths, working together to prevent any devastating collisions. The significance of resonance in maintaining stability can't be exaggerated. It provides a great example of how systems in space, even those that initially seem turbulent, can self-regulate through subtle gravitational forces. Understanding this resonance also explains why Pluto, despite its sporadic orbit, has remained stable for billions of years. This dynamic is a crucial part of the larger structure of the nearby planetary system. The effects of planets like Jupiter, Saturn, and even Uranus are essential in maintaining stability in the orbits of smaller bodies like Pluto. Jupiter, with its immense gravitational power, acts as a kind of guardian for the interplanetary system by influencing the orbits of various asteroids and dwarf planets, including Pluto. In fact, some analysts speculate that Jupiter's gravity could have prevented Pluto from being ejected from the nearby planetary group entirely. Without Jupiter's protective influence, Pluto's orbit might have been disrupted even further, potentially sending it out of the Sun's gravitational reach.